said in the last class, today we are going to start with complex logarithm. Okay, so of course you had to in the last lecture that you know how one defines the logarithm on the real line. So what one does is that one takes the exponential function which is defined on R, taking values in non-negative positive real numbers. So then what one takes is the inverse of that function. Of course that function was injective, and then one defines logarithm as inverse of the exponential function. Okay, so of course our basic idea of defining complex logarithm would be similar. We would like to start with the exponential function, and we would like to define a function which is kind of the inverse. So what do I mean by that? So by this I mean, so we are looking for a function f of z such that I am not saying the domain at this moment, but some function f of z such that e power f of z is equal to z. Okay, so that is what ideally we would like. Okay, and of course, as I said, I have not mentioned anything about the domain so far. Okay, so we are trying to get such a function. So first of all, now coming to the domain, let us try to understand. Clearly we know e power, let's say alpha is not equal to 0 for all alpha in C. So that implies that we can define logarithm only for non-zero complex numbers. Okay, so we can define f only for z not equal to 0. Sure, yeah, we can't have any this logarithm which is defined at the point z equal to 0, right? So therefore we only have to take non-zero complex number. Fine. Okay, and exactly what I had told you in the last lecture, that this function f is not unique. Okay, so choice of f is not unique. Okay, so what do I mean by that? Because we have seen already that exponential function is not an injective function. So for every point like which is in the range of exponential function, I might have several pre-images. In fact, there will be infinitely many of them. Okay, so choice of f is not unique for any such f, f plus 2I by k for k in z is also satisfies the desired property. All of you agree to this? Yeah? Yes?
Yes.
Okay, great. So, fine. So we understand that we will not have a unique function. So we are going to have this extra bit of thing, which is going to be always like it might get added up and all that. So, okay, fine. We will accept that much, and then let us nevertheless see if we can still define a function satisfying this property for all non-zero complex numbers. Okay, so we have to do that. So how do we do it? So we want to understand in terms of real parts and imaginary parts. Okay, we would like to see what should be the real part, what should be the imaginary part, and all that. Fine. So to define f, right, f as u plus iv. So where standard notation, u is the real part, v is the imaginary part. Okay, so if I write it like this, then what do I need? I need e power f of z is equal to z. So I need e power uz times e power ivz must be equal to z, right? E power uz plus e power I times e power ivz must be equal to z. Agreed? Yeah? Yes?
Yes, sir.
So here you should notice
Yes,
that
sir.
this u and v, these are real valued function. Okay, so this is purely a real number, and this one is like it's a complex number, so which is e power ivz. Fine. Okay, great. Now what do I do? It should remind you immediately of, like as I said, this is a real number, purely a real number, and this one is some e power I times some real number. So this should immediately bring the polar representation to your mind. So let us do that. So write z is equal to r e power I theta. Okay, so here for example we had said that initially in the beginning we are going to stick to one choice of theta. Okay, so means or in one range. So let us fix that theta belonging to minus pi to pi. Okay, so let us keep it like this. So I write it like that, and therefore what do I get? So here of course you should write that this r is the absolute value of z. Okay, so if I write it like this, then if I compare these two things, what I am going to get, I am going to get, so we get, I must have e power uz should be is equal to r. Okay, sorry, r, which is equal to mod z. So that implies what? Now you notice this is a real valued function, and I have that e power uz should be equal to r, which is equal to mod z. So that implies that I should have u of z, which is a real valued function, should be, tell me what it should be. This is now equal
Log.
real number.
Log of Z.
Very good. So u z
What is it?
log of mod z, not
Mod.
exact mod z. Fine, so we got hold of this thing, and here you see I don't have absolutely any ambiguity. Okay, because notice this is real logarithm, real exponential. I have absolutely no problem. This one is uniquely determined, absolutely no problem. Okay, and of course I had started with some z which is not equal to 0, we have already said. So therefore your mod z is a non-zero, rather positive real number, so therefore I can define what is a log. Great. Now, what about V? What can I say about V? So I have here, so what do I have the equality? E power I Vz must be e power I theta. So that implies Vz should be, tell me, this would be theta plus 2I pi k for some k in Z. Right? Fine.
Sorry,
There is no
sorry, theta plus 2 I would.
I. There is no I, 2 pi k. Okay, so Vz is theta plus 2 pi k. Fine. All of you agree to this? Yeah. Okay, and now remember I had taken my theta from minus pi to pi plus pi. Okay, so if my theta is in this range, then what the name we gave for theta? Do you remember?
Principal argument.
Argument. So principal argument rather. So capital R Z plus 2 pi k, like this way. Okay, so therefore great, I have now got a value for uz, a value for a choice of uz and choice of vz. Of course we understand the choice of uz is unique but not the choice of vz. So therefore what we have, hence we get f of z must be log of mod z plus I times argument of z plus 2 pi k. Okay, so this is the choice that we are getting, and of course you can see that here in the imaginary part I have this plus 2 pi k, I times 2 pi k floating around, and this is what we had agreed upon already, that logarithm will have several choices where the translation will be like this kind of thing. Okay, fine, so we can of course make a specific choice because exactly like argument we had taken a specific choice. So here also we could take a specific choice, and so put k equal to 0 and set, for example, log of z is equal to log mod z plus I times argument of z. Okay, So here, of course, remember my argument belongs to, this is the principal argument. So this belongs to minus pi to plus pi. One side open, one side closed. Okay, great. Now I have got a definition, fine, which one can work with. But and of course, from the construction itself, if I take e power log z, I am going to get z. Okay, so that's immediately from the construction. I don't have to do anything to check that particular identity. Now, the moment we define some functions, or especially in the context of complex analysis, when we are defining, our basic requirement would be whether, when I am defining a function like this, whether it is continuous, for example, whether it is differentiable or not. So all these kind of questions are very natural. Okay, so now, as I said, the question is this logarithm continuous? Okay, so what do you think? Is this logarithm going to be continuous the way we have defined? So I can define for all z not equal to 0, let's say. What do you think?
Sir,
Will this be a continuous function?
सर log of mod z सर मतलब रियल और इमेजिनरी अलग अलग देखेंगे तो सर log of mod z तो हो जाएगा लेकिन आर्गुमेंट ऑफ z में दिक्कत है
Exactly. क्या दिक्कत है? Yes. What kind of problem can we have?
क्योंकि सर इसकी जो रेंज में मतलब माइनस पाई से क्लोज पाई तो सर मतलब क्योंकि ये वैल्यू तो पाई देगा तो मतलब वो क्लॉक वाइज हाँ मतलब सीक्वेंस से
Okay. Go on. You're on the right track.
तो सर मतलब सीक्वेंस की वैल्यू तो माइनस पाई आएगी लेकिन सर जो उसकी वैल्यू होगी वो पाई आएगी सर कॉन्टिन्यूस
ठीक है, great. So that's a good point made by Nitin. So of course log mod z, I don't have to bother about that. That one is anyway on the r, so r plus. So that thing is continuous, fine. But this argument guy, this is not continuous function. That's a very good point made by Nitin. So exactly that is the problem which we are going to encounter for the logarithm as well. Okay, so let us see what he was trying to say. So let me draw a picture, and then it will be much very easy to notice. So let us have the coordinate system in place, and let us have the circle. Okay, so we said we are going to allow, for example, sorry, minus pi to plus pi. Okay, so you see, that means I am saying the point over here that has argument plus pi. Okay, now why argument is not a continuous function? For example, if you take the points which are like approaching pi, so or this point, that particular point, so let's not write pi, let's write a. So this is a is the point where the circle meets the negative real axis. And now you see, if I take a sequence of an, okay, which are means like below a, and it's approaching a. Okay, so let's say, let me write a1, a2 if that helps. So let's say this is a1, this is a2, this is a3, and so on and so forth. Okay, so we are approaching the point a from below. And then what do we see? We see that if we take the argument of each of these a1, a2, a3, they are rather close to minus pi. Okay, so when a1, a2, an approaches to a, their argument will approach to minus pi, whereas argument for a is plus pi. That is what we have taken over here. So this clearly shows that the argument, whatever choice that we have made, this is not going to be continuous. And it does not matter if, even if in place of minus pi to pi, if I would have taken this one closed, still there would have been a problem. Or if I would have taken, let's say, 0 to 2 pi, still there would have been a problem somewhere. Okay, so in general, the argument function for z not equal to 0 is not a continuous function. All of us agree to that? Yeah, yes or no? Do we all agree that logarithm is therefore is not a continuous function because the argument is not a continuous function? Yes. Tell me if you have not understood, I can repeat. So it's important that you respond.
Yes, sir. Repeat.
Yes, sir. Please repeat.
Yes, sir. Please repeat.
Please repeat.
Okay, so let us see. If you want me to write this point, so let us say a is a real number, so negative real number. So a belongs to R. Now what I am going to do, I am going to take this point. So here, of course, I have to take R e power I theta. So here R I will take R is equal to mod A, and then e power I theta. What I will take e power minus I minus pi plus 1 over n. Okay, so let me take an to be this guy. Fine. So this is my an, and do you see that an converges to a here? Yeah, if n tends to infinity, then your exponent is going to go to minus pi, and you know exponential is a continuous function. So e power minus I pi, which is equal to what? E power minus I pi is minus 1. So therefore, here I have written mod a, and a is negative. So mod a times minus 1 is going to give me minus a. So an approaches to a as n tends to infinity. Agreed?
Yes, sir.
Yeah. So this is on the negative real side. So r a is belongs to r less than 0. So an converges to a. Fine. Now what I am saying is that look at the argument. Okay, so by virtue of saying that my principal argument belongs to minus pi open to plus pi closed, so therefore what is the argument at a? What is argument of a? Tell me, what is argument of a? Tell me, what is argument of a? Pi, because I can, for example, write a as mod a times e to the power I pi. E to the power I pi is also minus 1, right? So mod a plus mod a times e power I pi. So therefore argument of a is pi. And what about argument of an? Argument of an is, tell me, what is argument of an? Just from the definition, what is it?
Minus pi plus 1 by n.
Minus pi.
So where does it converge to as n tends to 0 infinity?
Minus pi.
Minus
Minus pi.
pi.
Into minus 5, right? So therefore you see I have got a sequence where the sequence actually converges to a, but their argument is converging to minus pi, whereas argument of a is plus pi, right? So therefore what we see by the sequential definition, that argument is a continuous function. Agreed? Yeah.
Yes, sir.
Yes, sir.
Therefore, if you like just draw this picture, it will be immediately clear that argument, capital argument or the principal argument is not a continuous function. Okay, so therefore, if capital argument is not a continuous function at this point a, so logarithm is also not possible. It's not possible that logarithm is also, means like we will have that logarithm is also not continuous. Okay, now you see here I have nothing specific about a. A could have been any point on the negative real axis, right? For example, here I had drawn this circle and got that. I could have drawn a smaller circle and I would have got a different point, let's say a different point a prime. And the proof would have been the same, that the argument function or the logarithm function is not continuous at a prime, right? Do you agree to this? There is nothing special about
Yes, sir.
whatever negative point on the negative real axis I take, by doing the same kind of trick, by drawing a circle which is centered at 0 and passing through that negative point, I will always be able to show that okay, the argument is not a continuous function. So therefore what I see on this whole line, the argument is not going to be a continuous function. Agreed?
Yes, sir.
And which will in turn give us that on this whole negative real axis, or like of course 0 is already excluded, so on this whole negative real axis, but I can say that the logarithm, the way we have defined here, is not continuous. Correct? Yeah, yes. No.
Yes, sir.
Yes, sir.
Now, of course, you might say that, sir, you had taken a specific choice here, k equal to 0. So now, for example, you yourself tell me that in place of only the argument, if I would have added some 2 pi k, some let's say 2 pi or 4 pi or 10 pi, 12 pi, means would there have, means like, will there be any difference? Means if I make, let's say, I don't take the principal argument, but let us take some argument plus some 2 pi I or 2 pi k for some integer k, then will there be a difference? Will like that make logarithm to be continuous?
No, sir.
No, right? It's just, I'm just scaling one discontinuous function just by another scalar. So that scalar is anyway, it's a continuous function. So you can forget whatever happens to the original function. If you translate it by just some number, that's going to happen. The same thing is going to happen for that function as well. Okay. So therefore, whatever the choice of k that we make, I am not getting my log to be continuous on the negative real axis. Okay, fine. So of course, that tells us that, okay, if at all we have to look for a continuous logarithm, we have to let go this negative real axis. Okay, in fact, I will tell you something much more than that. You can in fact let go one of the rays. Okay, so what do I mean by that? So here, of course, I had taken a specific choice of logarithm, mainly the principal logarithm, where the argument, sorry, principal choice of argument, where the argument was varying between minus pi and plus pi. And then I said, okay, you forget the negative real axis, and then you can make your argument to be continuous or logarithm to be continuous, and so on and so forth. At least you do not know whether it's continuous or not, but the immediate problematic points you have removed, that you have been able to do. But it turns out that the negative real axis has nothing, it's not very special, in the sense, if I want, I can actually like I can see that there will be point like in the whole complex plane, there will be at least one line, no matter what choice of argument I take, no matter what choice of k I take, there will be at least one line where the logarithm is not going to be continuous. Okay, so what do I mean by this? So for example, as I said, we fixed choice of argument from to be, why it's not writing, so this one to be from, so I said that the choice of argument is from this interval, but even without that, but if we take some other argument, okay, some other argument from some interval, let's say theta to theta plus 2 pi, okay, for some theta, any theta that you wish. Okay, then what will happen? Then this new argument function will not be continuous on the line joining 0 and like on the line starting from, let's say, starting from 0 through e to the power I pi, sorry, e to the power I theta. Okay, so the point is, you can take any choice of argument, not only principal argument, you can take any choice of argument, saying that, okay, all you know is that argument needs to, like, you need to have this value of argument in a length of in an interval of length 2 pi. So let's take any theta, some real number, and then you consider, you say that we allow our argument to take value between theta to theta plus 2 pi. And then also you will still have the same problem, where you will not have continuity of your argument on the line which starts from 0 and goes through e power I theta. So for example, I can draw a similar picture over here. Let's say this is the coordinate system, and let's say I have the circle over here, and let's say this is my point. Okay, so this is the theta angle. Okay, so this angle is theta, let's say. So then what it says is that you should consider this line, and in this whole line, I don't want to draw too big. So in this whole line, the argument function is not going to be continuous. So you definitely need to remove this line in order to make your your argument function to be continuous. Okay, so it has nothing to do with the negative real axis only. Negative real axis is important to take, like to remove if you want to take the principal argument. Okay, so like that is why you will later call it a principal branch of logarithm. But anyway, you can in fact remove, means like you can, like no matter what kind of argument you take, always there will be a line which will be problematic, and in order to make your function continuous, you will your argument function to be continuous, you will have to remove this one line. Okay, so therefore we understand that we need to make sure that some line has to be removed anyway from complex numbers starting from 0, and then line segment starting from 0 and then going through e power I theta. Okay, so for example, if theta is equal to minus pi or pi, whatever it is, so that line is nothing but the line joining 0 and going through -1, line which starts from 0 and going through -1, so which means the negative real axis, exactly what I had over here. Okay, so therefore now I hope you understand that if I want to deal with this argument function, and therefore by means of that the logarithm function, I need to get rid of one line at least. Okay, so is this clear?
Yes, sir.
Okay, fine. So therefore now what do I have to show? Next I will do, so I'll define what is called a branch of logarithm. So definition. So what is the definition of a branch of logarithm? Branch of logarithm. Okay, so we for a domain D, or we say if okay, that a continuous function f defined on a set D on a set or open set, whatever you want, on a domain, let's say on a domain D, to be a branch of logarithm if we have, for all z in D, we have e power f of z is equal to z. Okay, so what do I mean by branch of logarithm? By branch of logarithm, what we mean is that we should have a continuous function on the domain D such that for all points in that domain, e power fz should be equal to z. Okay, so of course here the things depend on D. So for example, if somebody tells you that can I have a branch of logarithm on c star c minus 0, then of course we have seen already that it's not possible. Okay, so on c star there does not exist any branch of logarithm. Okay, so whereas for example, if I take some other subset of C, like the ones which we had taken, in those kind of sets, we can perhaps define a branch of logarithm. Okay, so let me do that. And so, for example, if we take, so let's say my D is this set R e power I theta, such that R is positive, and I take theta in certain so theta belonging to, let's say, some interval alpha to alpha plus 2 pi. for some alpha in R. Okay, so I can take such kind of a function. So like okay. So if we take D like this, then we can perhaps define continuous logarithm on D. Okay, so perhaps it is possible on these kind of sets to define a continuous logarithm. Okay, and of course, once I have one continuous logarithm, there will be several copies of logarithm just by adding some 2i pi. Okay, or integer multiple of 2i pi. So therefore, once I have a branch of logarithm, then immediately I will get several other branches of logarithms. Okay, so in such kind of sets, perhaps we can define logarithm in that way. Okay, and of course, now you need to show that in this kind of a set, the way you can define logarithm, that becomes continuous. Okay, so that I will leave as an exercise. Okay, so exercise, show that f of z defined as f of z is equal to log of mod z plus I argument of z, where argument of z belongs to alpha to alpha plus 2 pi, is a branch of logarithm on the above set. Okay, so you can show that once I have removed this one line, then whatever the set I have in that set, the argument function becomes continuous, and therefore, or like for example, if you don't want to complicate your life, you can just take the principal argument and you can remove the negative real axis, and then you can try to show that whatever logarithm I have defined over here, this one is continuous on the set like r e power I theta, r positive, and theta between minus pi to plus pi, both side open. Okay, so in that set, this logarithm is going to be continuous. Okay, so that is something which I am leaving you to show, for you to show. Okay, so it's just a matter of showing that the argument is going to be continuous at all those points. Okay, because what essentially the means, like the proof, what it involves is that if you take any other point, let's say in this picture, if you take any other point which is not on that line, you will always be able to find a small neighborhood around that ball which is completely inside your domain. Okay, so it's not going to intersect that. Anyway, it's an open set. So you will always be able to stay away from that line. Okay, it's not going to cross that line, so you can stay away from that line, and in this neighborhood, of course, you can give some argument to show that the whatever argument function you define, that's going to be continuous. Okay, so anyway, this is what is a possible branch of logarithm. Okay, so that's number one, and of course we know that this is easy. Or let me continue here. Then g of z defined by f of z plus 2i pi k is also a branch of logarithm, okay, on D. Okay, so this is also a branch of logarithm on D for any k in z. Okay, so if I have f to be defined like this, so then this f of z is of course a branch of logarithm. But if you just define a new function g, which is just translated by 2i pi, that is also going to be branch of logarithm. Okay, so what is the branch of logarithm? Branch of logarithm is a continuous function defined on some domain D such that for all the points in that domain, e power fz should be equal to z. Okay, so clearly we understand that set of sets of the form D like c minus 0. So for example, if I take D equal to c minus 0, then such kind of sets cannot have a branch of logarithm defined on that set. Okay, is this clear, whatever I have said so far? Yes.
Yes, sir.
Okay, fine. So prove this one. Now, of course, we understand that if I get an f, which is a branch of logarithm, then if I translate it by 2i pi, then that's going to be another branch of logarithm. Okay. Now you can ask whether these are all possible branches of logarithm or not. Okay. So, for example, if I start with an f, which is a branch of logarithm, if you add 2 pi I, so that's going to be another branch of logarithm. Now the question is it true that all branches of logarithm on that particular given set arise in this way only? Okay, so that's the next theorem which we are going to prove. So theorem. So remember, when I have branch of logarithm, it is important that that comes with a set D. Okay, so the D is also there. Okay, so of course if you change the set D, the function itself changes. Of course they can be same in the intersection and all that, but generally whenever I define a function, it comes with a set domain, so we stick to that. Okay, we do not change the domain suddenly. Okay, so what I am saying here, so if f is a branch of is going on. Yeah, if f is a branch of logarithm on D, on a domain, let me write, on a domain D, then any other branch of logarithm on D is of the form f of z plus 2i pi k. Okay, so any other branch of logarithm is going to be of this form for k in z. Yeah, so what I am saying here, of course, if I add by plus 2i pi k, that's going to, when I take exponential, it's not going to contribute to anything, and then so therefore I will like all of them are branch of logarithm. But as I said, it turns out that any branch of logarithm is going to arise only this way. Okay, so there is absolutely no other choice for us. We must have, so once I have one branch of logarithm in my domain, I will know all other branches of logarithm would be just translate of that function, and that to translate by 2i pi times some integer multiple. Okay, so these are the all possible choices of branches of logarithm on D. Okay, so how do I do this? Let's get to the proof. Fine. So let G be another so let G be another branch of logarithm on D. So I'm starting with another branch of logarithm. So what do I get by definition? So we get that e power f of z is equal to e power g of z is equal to z on D. Okay, so I have this. Fine. So now what I am going to do, I am going to fix one particular z naught, and then I'm going to write down the same identity. Okay, so now for a fixed z naught in D, we have e power f of z naught equal to e power g of z naught, okay, which is of course equal to z naught. Okay, so for any fixed z naught, this is true, so I am writing it for one z naught. Okay, so what can I say about f of z naught and g of z naught? What do you think? What can I say about them? Yeah, tell me. Yes, what can I?
With the difference of multiple of 2 pi.
Very good. So at this point, what I can say, so there exists k naught in z such that e to the power, such that f of z naught is equal to g of z naught plus e to the 2 I pi k naught. Okay. So at least at this for any fixed number, any fixed z naught, I have this particular phenomenon. Okay, at least means the k naught might depend on z naught, but I am going to get f of z naught equal to g of z naught plus 2 I pi k naught. Okay, so that's just from the property of exponential function. Okay, so now I want to show whatever that g is the same, g is a branch of logarithm which is just f of z plus 2 I pi. So what I have to show here is that we need to show that this k naught works for all z in D. Okay, so if I can show that this k naught works for all z in D, will you agree that we get that g of z is nothing but some translate of f of z by some integer multiple of 2 I pi. Yeah.
Yes, sir.
So if we can show this, we are done, right? So we need to show that k naught, this k naught, or let me write rather, we will show that the k naught works for all z in D. Okay, fine. So I'm going to show that this k naught works for all D. Okay. Anyway, now let me write. Yeah. So anyway, tell me this one. So if I consider the following function, consider f of z minus g of z divided by 2 I pi. Okay, so on D. So can you tell me what is going to be the domain, going to be the range of this function? So what will be the values of this function? What kind of values do I get if I consider this function? F of z minus g of z divided by 2 I pi. What kind of values this function will take?
Integer.
Only integers, right? Consider this function. This only takes integer values. All of you agree to this? Yeah?
Yes.
No, because no matter what point from z you take, you know that e power fz is equal to e power gz. So fz minus gz will be some integer multiple of 2 I pi. Okay, so that what is the integer multiple that might change. I am not bothered about that, but whatever it is, f of z minus g of z divided by 2 I pi is going to be a function which takes only integer values. Correct? All of you agree to this?
Yes,
Yes.
sir.
Yes, sir.
So this takes only integer values. Now what do I have? I have that f and g, these are continuous functions. So this function, so I did not give it a name, so let us call it h. Okay, so h of z is equal to this one, let's say. So then tell me, so can I say about continuity of h anything? So can I say anything about the continuity of h? Yes. By definition,
Yes, sir. Continuous.
also continuous on D, because why? F and G both are continuous, right? They are branches of logarithm, so therefore they are continuous, isn't it? That's by definition, right? So by definition, branch of logarithm means I must have a continuous function. Okay, so by very definition, f and g are continuous, so therefore what I get, h is continuous. Okay, now D, I started with a domain, so that means D is a connected set. So what can I say about h of d? So this is a general theorem.
Connected.
Yeah, if you have already seen it in topology, that's good. But if you have not seen also, so it's not very difficult to prove that just from the definition itself, definition of continuous function, it's easy to prove that continuous image of connected set is connected. Okay, or like whatever you had seen in real analysis intermediate value theorem, continuous image of interval is interval, exactly same thing. Continuous image of connected set is connected. Okay, so if the image is not connected, you will be able to write the image as union of two disjoint open sets. You can take their inverse image. Since H is continuous, by definition of continuity, you will get that their inverse images are going to be open sets. And since these two open sets on the right, if you take their union, it gives you h of d. So when you take inverse image, you get two disjoint open sets whose union is going to be whole of d. Okay, so therefore, since d is connected, you must have h of d to be connected. Fine, all of you agree to this? So there's a small fact from topology, but it's not very difficult to prove. It is just from the definition that continuous image of a connected set is connected. Fine.
Yes, sir.
Okay, so now tell me what are the connected subsets of Z. So h of d is a subset of Z.
Singleton.
Yeah. Now h of d is a connected set that we know, and we have seen h of d is subset of Z, and the connected subsets of Z are singletons. Okay, so what singleton set this should be? So h of d is equal to which set? Tell me.
Set of integer.
No, which set? Like it's a singleton.
Singleton K naught.
So h of d is k naught, because k naught I already know that this is in the image, right? Because for example, at the point z naught, h of z naught is k naught, and I know that h of d must be a connected set, a subset of z, and connected subsets of z are just singletons or empty set. People call empty set to be also connected, but anyway, here non-empty connected sets. Let me write non-empty if you wish. H of d is k naught. So the same can. So the same cannot works for all the points in D. Okay, fine. All of you therefore agree to this proof. Okay, so f of z minus g of z divided by 2I pi is equal to k naught for all z in D. This implies g of z is equal to f of z minus 2I pi k. Fine. So are we done with this proof? Yes.
Yes, sir.
Fine, great. So therefore, we see that this thing is going to be that any branch of logarithm, if you choose that, like, or one says it in this way, that any difference of any two branches of logarithm on a given particular set is like means two branches of logarithm on a given particular set differs by an integer multiple of 2I pi. Okay, great. So now I am going to so all these are done. So we understood what is a branch of logarithm, and exactly we were started our discussion by saying that we would like to understand the property of this logarithm function. So we want to define it in, of course, in first of all in a continuous way, and now our aim would be to show that this logarithm function that we have defined, that is actually going to be a holomorphic function. Okay, so wherever we can define it, we will say that it's going to be a holomorphic function. So how do I get holomorphicity of the logarithm? So the holomorphicity of the logarithm we are going to get by means of the following theorem. Okay, so let us see what is the theorem. So this is a more general statement, we are going to use it. Okay, so what is the general statement? So let UV be two open subsets of C. Suppose f from U to C and g from V to C be continuous functions such that I have f of U is subset of V and g of f of z is equal to z. Okay, so I have g is such a function that g of f of z is equal to z for all z in U. Then if g is holomorphic and g prime does not vanish on V, then what I can say, f is holomorphic. So if g is holomorphic, let's say on V, and g prime does not vanish on V, then f is holomorphic on U. And I can also talk about what is the derivative. F prime of z is going to be equal to 1 upon g prime of f of z. Okay, so this is what I'm going to get, and we have this particular theorem. Fine, so what am I saying here? I am saying that I have two open subsets. I have two functions defined on each of them, which are continuous functions, and with the assumption that, of course, f of U, the image of f is inside the domain of G, so that I can essentially compose G and f. So if G composed f is the identity function with the property that G is holomorphic and the derivative does not vanish, then f is also going to be holomorphic and the derivative of f is given by 1 upon g prime of f of z. Okay, so here as a corollary we get branch of logarithm are holomorphic. Okay, so no matter what branches of logarithm you take, they are going to be holomorphic, and that is independent of the domain, of course. Okay, so here let me just quickly do this. So for example, if I take of course and which of logarithm are holomorphic and their derivative is, so what do you know what is derivative of log of x, for example, in real line? What is derivative of log of x?
1 by x.
Here also I'm going to have, no matter what branch you take, no matter what domain you take, for all of them they are going to be holomorphic and their derivative is going to be 1 over z. Okay, so that's a let's quickly see the proof of corollary. Okay, then we will talk about the general theorem. Okay, so what is proof of corollary? So for example, if I take, so let g equal to x. Okay, so g is the exponential function and f be any branch of logarithm, okay, on any set that you choose. So by definition, branch of logarithm means I am taking a continuous thing. Okay, so let g equal to this and f be any branch of logarithm. Then what can I say? I will be able to say that, for example, we know by definition e, or like e to the power fz I was writing, so exponential of fz is equal to z. That is what we have, and that implies that f is holomorphic, as we already know exponential is holomorphic and non-vanishing, and non-vanishing. Okay, so here of course the g prime needs to be non-vanishing, but if you take the exponential function, its derivative is itself, so exponential is holomorphic and this is non-vanishing, so therefore we get g is holomorphic. And we have what is derivative? Derivative of f prime of z is 1 upon exponential of f of z, right? Derivative of exponential is exponential. Now exponential of f of z is just z, So therefore 1 upon z. Fine. Are we done with the proof of the corollary? Yes. Do you agree to the proof? Yeah.
Yes, sir.
Yes, sir.
What we see that of course branch of logarithm we started with a continuous function, but it turns out that the branch of logarithm, like you choose any branch of logarithm, that's going to be even holomorphic in whatever domain it is defined, and the derivative is going to be 1 upon z. Okay, so therefore this particular fact comes up easily from this particular theorem, and so therefore we are going to prove this theorem now. Fine. So let us go to the proof of this particular theorem. Okay. So proof of theorem. So proof of theorem. Fine. So first of all, let us observe the following few facts about our functions, and then we will see what is to be done. Okay, so we have g composed f of z is equal to z. Okay, so on this is on u, because u is the domain of f. So I have this is on u, and this implies f must be injective. Okay, injective on u. So f is an injective function on u. Agreed? Yes?
Yes, sir.
Okay. Now what we are going to do is that I have to show two things. One is f is holomorphic, and also in the theorem there was this candidate of derivative. So I have to show both the things. So therefore what we are going to do, we are going to prove this simultaneously. In the sense, how am I going to do? So for a in u, we show that limit h tends to 0, f of a plus h minus f of a divided by h exists and equal to 1 upon g prime of f of a. Okay, so here we take h such that a plus h is also in u. Okay, of course I need to define what is my function at a plus h. So once like of course since u is an open set, generally we are taking domains, right? So here, yeah, domain. So therefore everything is open here anyway. Yeah, two open sets. So since u is an open set, and or open here a is a point in u, so of course there will be a ball around a which will be contained inside u. So of course as h tends to 0, a plus h will tend to a. So therefore eventually we can make sure that a plus h belongs to u. Okay, so this quantity f of a plus h, that is fine, like there is no problem. Okay, so we have to do this, right? Clear what we need to do? Agreed or not? Tell me. Hello? Are you with me? That if we do this, we are done.
Yes, sir.
Okay, great. So now you tell me one thing. H tending to 0. Okay, of course, generally we will not take h equal to 0, right? Here, because I'm going to get 0 by 0 thing, and so we are not going to take h equal to 0. So h is not equal to 0 and h is going to 0. Okay, so if since h is not equal to 0, we have, of course, this quantity f of a plus h is not equal to f of a, as f is injective. Correct? So since f is injective, I can say this, isn't it? F of a plus h is always not equal to f of a. Yeah?
Yes, sir.
What I am going to do, I am going to write down this ratio f of a plus h minus f of a divided by h in a different sort of way. So let us see, how do I want to write this? I want to write this as g of f of a plus h minus g of f of a divided by h on the numerator. In the denominator, I have g of f of a plus h again minus g of f of a, and then in the denominator I put f of a plus h minus f of a. Fine. Will you agree to this if I write like that?
Yes, sir.
So of course whatever I had over here I have put it over there, and in the numerator and denominator I have just put this g of this whole thing. Okay, so tell me what is the numerator now? What can I say about this quantity? Quickly tell me, what is this quantity?
1.
Very good. This quantity is nothing but 1. It's not going to 1. This is actually equal to 1, right? Because this is nothing but a plus h minus a divided by h, isn't it? So this quantity in the numerator is equal to 1. I don't have to bother about that. Fine, let us look at the denominator now. Okay, now what is my denominator? My denominator is g of f of a plus h minus g of f of a divided by f of a plus h divided by f of a. This is what I have to figure out. What is this guy? Fine. Note. So yeah, I can just remove this. Note. As h tends to 0, where does f of a plus h go to? Tell me.
F of A.
F of A.
Why? Why does it go to f of a?
S tends to 0.
Yeah, as f is continuous, right? I had started with this assumption on f to be continuous. Okay, so these are continuous functions we had started with. So f is continuous, so f of a plus h goes to f of a. So therefore, now can you tell me where does this ratio go to? So this ratio essentially looks like, so that term that we had, so like I had whatever I had removed. So this quantity I can write like this is g of some, let's say alpha h minus g of alpha divided by alpha h minus alpha. Okay, and what is alpha? Alpha is f of a. Okay, so where alpha is f of a and alpha h is f of a plus h. So what do we say? So if h tends to 0, where does this ratio go to? Tell me.
G
Yeah?
prime of alpha.
G dash alpha.
Now if h tends to 0, we have alpha h going to alpha. So g of alpha h minus g of alpha divided by alpha h minus alpha going to g prime of alpha. Okay, now what is my alpha? My alpha is f of a, so this is g prime of f of a. Very good. So therefore this was my thing which I had to estimate. The numerator goes to 1, or it is equal to 1 anyway, and the denominator goes to g prime of f of alpha as h tends to 0. And remember, I have g prime is non-vanishing. Okay, so this term goes to g of alpha, so this and this is not equal to 0. It is given. So what can I say? Where does this term go to? G of alpha h minus g of alpha divided by alpha h minus alpha. So this goes to, if I take the reciprocal, that goes to 1 upon
1 upon G prime F.
G dash F of A.
alpha.
Alpha.
So whatever g prime of f of a, let me write that directly as h tends to 0. Correct? So of course this is important, because unless if g prime of alpha would have been 0, the reciprocal does not have a limit, like, or it could be infinity and all that, or it could be oscillating, things like this. But anyway, now that the g prime of alpha is not equal to 0, I can definitely say that the reciprocal is going to g prime of f of a. And what is this reciprocal? This reciprocal we have just seen, this is nothing but f of a plus h minus f a divided by a plus h. Okay, and divided by h, sorry. So this is nothing but that, and as h tends to 0, so therefore we see that f of a plus h minus f of a divided by h goes to this, that is limit h tends to 0, f of a plus h minus f a divided by h is equal to 1 upon g prime of f of a. Agreed, all of you? Yeah.
Yes, sir.
Yes, sir.
Remember here, this limit became g prime of alpha because g in our hypothesis was holomorphic. So the g is differentiable. So therefore, at alpha we could get this, and of course we had used continuity of f. Eventually, with all this, I get this is what is our formula. Okay, so therefore we our the general theorem that I had stated over here, that theorem is proved, and thereby the holomorphicity of the logarithm function is also proved. Okay, so let me just give you few means like small other facts about the logarithm function. So I will start by defining what is the principal branch of logarithm. So we have seen the principal argument. So similarly, there is a principal branch of logarithm. Okay, so what is that? What is the principal branch of logarithm? So the logarithm, which as I said, it was going to use the principal argument, and it's going to be defined on the set of all complex numbers minus the negative real axis including 0. Okay, so the branch of logarithm defined on the set, the branch of logarithm defined on the set z equal to r e power I theta such that r is positive, theta between minus pi to plus pi open. So how the function is defined? The function is defined by log of z is equal to, by definition, log mod z plus I times argument of z, capital argument. Okay, so that's the definition. Defined by this is called the principal branch of logarithm. Is called the principal branch of logarithm. Okay, so that's, I have already told you that this is going to use the principal logarithm, principal argument, and of course we are going to remove the negative real axis including 0. The main point being, of course, we had a logarithm on the real line, and we would like to have means correspondence with that. Okay, so that is the reason why I don't want to change the argument. I want to keep the principal argument, and also I want to take exactly, for example, if I take this particular logarithm and if I restrict this particular logarithm to the real line, then this will be exactly the real logarithm that we have already, like that you already know. Okay, so that is the reason why one takes this particular logarithm, and it is called the principal branch of logarithm over here. Okay, so of course here you can see if I put z equal to r e power I theta, where theta is in the where theta is principal argument, of course you see this is nothing but log of r plus I theta. Okay, so anyway, we get this is the principal branch of logarithm, and I told you the main reason, like there are in means like the interest of considering this logarithm are like twofold, in the sense we have one thing that this is using the principal branch of principal argument, that's number one, and this particular logarithm is going to be equal to the logarithm that already we had seen in the set of real numbers or positive real numbers. So that's the reason one particularly looks at this particular branch of logarithm. Okay, so keep this in mind. Whenever I say principal branch of logarithm, I mean that I am looking at this particular set, and this is my definition of logarithm. Okay, so even if I, let's say, add a 2i pi, that will not be principal branch of logarithm. And even if I have the same definition without this 2i pi, even if I have the same definition but my set is slightly smaller than this set, it will not be called principal branch of logarithm. Principal branch of logarithm means that we have this particular set. Okay, so this set, if you try to draw a picture, this set will be the entire complex plane, so the whole complex plane except this line, okay, including 0. So you just forget that line, and then whatever remains, that is your set, and on that set you define in this way so that it matches the value at the real axis, positive real numbers. So this is called the principal branch of logarithm. Fine, is it clear, the definition?
Yes, sir.
Okay, great. So of course you remember I had told you that means our interest of studying holomorphic functions were in the sense that they means like we said that previously we gave some examples where holomorphic function, we saw power series as holomorphic functions, and then I had also told you that in general this is true. For any holomorphic functions we will be able to have a power series expansion. Okay, so of course exponential and those kind of functions were like defined in terms of power series, and therefore from the holomorphicity of the power series immediately gave that expansion already. So we started with power series there already. So here I have a function which I did not start with the power series. Okay, I just started by looking at some kind of an inverse of exponential, and we got that it's going to be it's going to be a holomorphic function. So what before going to, let's say, having a general theory of holomorphic function writing in power series, let us try to see if I can write down the power series expansion of the logarithm itself. Okay, so we are going to try to do that. Fine, so how do I do this? So let me write down that. So power series expansion of logarithm, or okay, so this is the next thing which or probably the last thing that I will be able to have time to do this. Fine, so what do I do? So recall, so let f be a branch of logarithm, or let us take this to be, yeah, let's take any branch of logarithm. Okay, so it's a branch of logarithm defined on some set. Okay, so we know the derivative of f is going to be f prime of z is 1 upon z. Fine, z is not equal to 0, of course. Okay, so what I am going to put is the following. Okay, so we put z equal to 1 plus w. Okay, so that is I'm writing f prime of 1 plus w is, or 1 plus omega, whatever you want to call, 1 upon 1 plus omega. Okay, so why did I write it like this? I wrote it like this for the very simple reason, because I can, so that I can expand it. Okay, so now we know what I know, 1 plus 1 over omega. I can write it as 1 minus omega plus omega square minus omega cube plus omega power 4, and so on and so forth. And this is something, this is going to converge for mod w less than 1. Okay, so I am going to have this, and this is going to make sense for mod w less than 1. Fine, yes, is this do you all agree to this?
Yes.
Yes, sir.
Great. Now what do I do? See, I need what we need. I'm looking for a function, so we need f such that I have f prime of 1 plus w is this given by this expression, or this, sorry, 1 minus w plus w square minus w cubed plus w power 4, and so on and so forth. So this is what I need. So I think the generic term will be minus 1 power n w power n. Anyway, so this is what I need, means I need a function f such that this is what happens. Okay, so let us go to the formal world and let us try to construct. Okay, so and see if I can get something out of it or not. Okay, so what we are going to do, so consider the formal power series. So what I need to do is that, you see, I know what should be my outcome once I take derivative. Here what I am wishing for is that I know the result after taking the derivative, but now I am trying to look for the ones which gave us this one. So what you need to do, essentially, you need to take the primitive. So if you take the power series, consider the formal power series x minus x squared by 2 minus or plus x cubed by 3 minus x power 4 by 4 plus so on and so forth minus 1 power n x power n plus 1 divided by n plus 1 and dot 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 dot. So we are going to consider this particular formal power series. How did I get get this one? Because I understood, like, in my mind I can see that if I take term by term differentiation of this particular power series, I'm going to get this one. Okay, and of course we have seen that if a power series converges, then its open domain of convergence, the differentiation of power series exactly works term by term. Okay, so this is what we have, and this guy has, what is the radius of convergence of this power series? Tell me, what is the radius of convergence for this power series?
1.
So you can just take the nth root upon taking absolute value. You are going to get that the radius of convergence is 1, or you can take ratio test, whatever you want to do. You will get that this has radius of convergence, this one. Fine. Okay, so now so if we set, so I want to set this, if we set f of 1 plus w is w minus w squared by 2 plus w cubed by 3 so on so forth plus minus 1 power n and w power n plus 1 divided by n plus 1 and so on so forth, then we see that f prime of 1 plus w is 1 upon 1 plus w. Do you agree to this? That if I take my little f of 1 plus little f in such a way that this guy, if it is like this, then f prime of 1 plus w will be 1 plus w. Yeah, do you agree to this? Because I can take term by term differentiation and I'm going to exactly recover this guy, correct?
Yes, sir.
Okay, so you see, I have chosen something, and like I have taken a formal power series, and the derivative is this one. So actually, if I think of the logarithm, okay, so therefore what I essentially have, that means my logarithm, whatever I should have, that one, and this power series, like, or let us say the function which is given by this guy, this particular power series, that can at most differ by a constant. Okay, because both of them are giving the same derivative. Okay, so whatever f, so here I wrote f in this way, so let me write g. Okay, so if we write, so that there is no confusion, let me write it like this. If we said g of 1 plus w is this, then we see that, let me write here. Okay, so g prime of 1 plus w is 1 over 1 plus w. So if I take this to be g of 1 plus w, then g prime of 1 plus w is 1 upon 1 plus w. So that implies what? That implies f prime minus g prime of 1 plus w. So this whole function of 1 plus w is identically 0, right? So therefore the derivative is identically 0 on a domain. So what can I say about the actual function f minus g? Tell me, what can I say about
Constant.
the function? So this function is going to, we have already seen using our CR equation and all that. So f minus g is going to be a constant function. Fine. So f minus g is the constant function. Now let us look at this function at like, for example, what is g of 1? Tell me, what is g of 1 from the power series? G of 1 is 0, like that means w, you have to put w equal to 0, so G of 1 is equal to 0. Now if f is the principal branch of logarithm, I started there with any branch of logarithm. Okay, so if f is the principal branch of logarithm, then what is f of 1? Look at the principal branch of logarithm and tell me what is f of 1. Yes, what is f of 1? That is also, yes, 0, right? I told you that the principal branch of logarithm is exactly matches with the logarithm on the real line that you already know. Okay, so therefore we already know now if principal f is the principal branch of logarithm, then f of 1 is also 0. So hence I must have f equal to 0, f equal to g, right? So f minus g is a constant and g of 1 is 0, f of 1 is also 0. So therefore f must be equal to g. So thus for z mod of z less than 1, we have log of z is equal to, we have the principal branch of log of z is log of 1 plus z, rather log of 1 plus z is equal to z minus z square by 2 plus z cube by 3 minus z power 4 by 4 plus so on and so forth, in general minus 1 power n z power n plus 1 divided by n plus 1 plus so on and so forth. Okay, so we can write, yeah, minus 1 power n z power n plus 1 divided by n plus 1, n bigger than or equal to 0. Okay, so this is the power series expansion of the function log 1 plus z, which is around 0. Okay, and around 0, z equal to 0, log of 1 plus z is having a radius of convergence 1, radius of convergence 1. So therefore it is valid in the neighborhood, like in the unit open unit disk around 0. But here the function is not log, here the function is log of 1 plus z. Anyway, so it's more convenient to write in this way, because so that I can just write the power series in terms of z. Of course log is not defined at 0, so therefore I have just translated it to like 1 plus z. So around the point 1 I have translated it, and I have got the power series expansion for the principal branch of logarithm. Fine, agreed? All of you are clear with this? Yes or no?
Yes, sir. Yes,
Yeah. So therefore we have got the power series expansion of the principal branch of logarithm, and we see this is around z equal to 0 for log of 1 plus z. Remember this, there is there is a slight difference. I'm not saying it is the expansion of log of z. Okay, so it's the expansion of log of 1 plus z around z equal to 0. Okay, so that means essentially I am expanding a log around 1. Okay, at 1 the function is 0 anyway. So with this I'll stop here. So I don't have time today to start complex integration. So in the next class we will start with complex integration. Okay, fine. So I'll stop the recording here. Are there any questions?